Hi, I'm Chris Kanich, and this is CS361, Systems Programming. Today, we're going to be talking about I/O multiplexing. So at the end of the last lecture, we're talking about this race car analogy that I have. It's very, very fast if you are going to use I/O multiplexing. This is used in many, many different locations, primarily in a lot of the web work that is done in the modern world, both in terms of raw web servers like the Nginx web server, as well as the JavaScript runtime, when we want things to happen as fast as they possibly can, when lots of little different events are going to be involved. I/O multiplexing is the right way to do it. But I/O multiplexing is much, much more complicated than a typical multi-threading or multi-process way of handling multiple tasks at the same time. And this is because when we use threads and processes, we're relying on the operating system to do all of the scheduling for us. As long as we're doing our task correctly, the operating system is going to say, okay, this program is going to run in this order, and I'm going to take it off, and then I'm going to run something else, and I'm going to bring that one back on, and that specific chunk of code doesn't even need to know that it got swapped out. It doesn't even need to know that other processes are running at any given point in time. And that's useful for us as programmers. When we think about getting a task done, we think about, okay, if I'm doing this one specific task, I do step 1, I do step 2, I do step 3. It doesn't matter that in the real world, I do step 1, I do step 2, I get pulled off, some other thing does step 1, does step 2, does step 3, it gets pulled off, I come back in, I do 4, 3, I do 4, etc. The operating system is going to take care of all of that interleaving for us so that we can think about our different instructions running one at a time with nothing else interrupting it. That is a fantastic way for us to think about things and for us to write correct code. But sometimes we want to say, I want to throw that away and think about things in terms of, I'm going to be in charge of deciding when to stop doing one thing and start doing another. I'm going to be in charge of saving my work for this one task and restoring my work from this other task. And this leads to more complexity in our code, but it can also lead to more performance. So the main workhorse behind I/O multiplexing is typically going to be something that looks a lot like select. So select is a little bit historical. It doesn't get used very often in the modern world. There are better, more efficient ways to do this, but this is what we've got in the book. And it does a good job of showing us the core element that drives I/O multiplexing. So what we have here is the select function. This is just straight out of the man page. We have our number of file descriptors. We have to tell select, listen, I have a numeric chunk of file descriptors. They start from 0, 1, 2, 3, 4, 5, etc. We have some maximum number that we're allowed to use. We need to tell select, listen, you only need to pay attention to the first 5 or the first 10 or the first 20. We don't want you to have to keep track of all 4,096 hypothetical file descriptors if I only really care about the first few. So I'm going to have that maximum number of file descriptors that it has to take a look at, the highest index that it has to look for. And then I'm going to have these 3 different file descriptor sets. So this FD set type is very important and interesting. And the fact that we're passing in a pointer is also very important and interesting. At its core, what select is going to do is going to put our process to sleep until something happens. And we tell the operating system what that something should be using these 3 arguments. We've got our read FDs, where we say, operating system, I'm going to give you a collection of file descriptors, and if any of them are ready for reading, wake me up. Then I'm going to give it a set of write file descriptors and say, operating system, if any of these are ready for writing, wake me up. And if any of them are in some exceptional state, like something went wrong, also wake me up because I'm going to have to deal with that as well. So one thing that we don't see too much in the assignment or in a lot of the coding that we typically do for this is this write file descriptor set. Why would we have to wait for writing? So we can go back to what we learned in the networking module about how when we call write or when we call send, what we're really doing is saying we have a buffer in our user level code. What we want to do is ask the operating system, hey, will you take these bytes and put them in your buffer so that you can eventually send them to wherever it is they need to end up at on the other side of the planet? And the operating system says, yeah, sure, okay, I'm going to accept these bytes from you in your user level buffer. I'm going to put them in my kernel level buffer, and I'm going to send them out into the world. What can possibly happen is maybe this connection out to the outside world is really, really slow. Maybe you've got a dial-up modem and it can't send things nearly as fast as your program can create them to get them to send out. So what will end up happening is your program will run really, really fast. It'll push things in, push things in, push things in, and then the operating system will say, listen, you cannot send any more bytes until I have finished sending these bytes to the other side of this really slow network connection. And that will cause your call to write or your call to send to block. What we are trying to do is make sure that our code never blocks unless we have nothing else to do. That's a really good kind of definition of what select is used for. Select allows us to do multiple things at a time and only pause our program when we have no other work to do and only be woken up whenever any work can possibly be done. So we can imagine, to go back to thinking about this write FDs, that we completely filled one of these buffers, and we know that we need to send more bytes. We still need to send 10 megabytes of data into that network connection, but the operating system is saying, hey, I'm full, you can't send anything else. What we can do is say, hey, operating system, I need you to tell me when this client talks to me, when that client talks to me, when that client talks to me, or when there's space in this buffer that I can give you more bytes to send to the other side. So that's the type of situation when we would add something to that write FD set, because we're filling up a buffer and it's possible that we're going to block rather than just submit those bytes to the operating system and have them send immediately. Because most of the time when we're writing our simple little programs and we're learning, we never have write block. Write is almost always just going to send those things as fast as it possibly can because there's plenty of space in the buffer in the operating system to hold on to everything we want to send and then send it out piece by piece. And then finally, also important, we have this timeout value saying, hey, operating system, you're going to put me to sleep. You're going to tell me if any of these things happen, but I know that I have work to do. I might have to write something out to a log file, or I might need to check for something else, whether a file has changed on disk that I don't check very often, like my configuration file or something. I want you to wake me up in 500 milliseconds, 50 seconds, 500 seconds, whatever it is, so that I can do whatever housekeeping I need to do, even though nobody talked to me, none of the buffers became unfull, and none of my file descriptors ended up in an exceptional state. That's going to be the core thing that we do in IO multiplexing, is going to be sitting there and saying select puts us to sleep until any of these things happen. And when any of these things happen, we need to say, I'm going to do a little bit of work for this task. I'm going to do a little bit of work for this task. I'm going to do a little bit of work for this task, and keep all of those tasks separate ourselves rather than relying on the process or thread abstraction that the operating system provides to us. So to get a little bit of an introduction to how select is working on the internals of it, we're over here in our handy dandy skeleton code for the assignment. And so if we come down here, we see that select is here. Now, we notice that this is capital S select. It's taking the same arguments, but it's just a little bit different. We can click through here. You can see that this is just a very simple wrapper that's going to check for an error that comes back from select. And if there is an error, it'll bomb out for us rather than just having it be a return value that we need to check every single time. So we can think of this as effectively it's going to work the same way that regular select would work. And we have the same set of arguments that we had talked about earlier. So we've got our maximum number of file descriptors, and we've got our read set that we have copied in here, as well as our write set, accept set, and our timeout. We have no timeout, which means that we're going to wait here absolutely forever till the heat death of the universe if nobody comes and talks to our server. That would be so sad. So at a high level, the important things that we care about here for select are really that we are in charge of keeping track of all of the different tasks that we're going to be doing using this code. And the way that we do it in this specific code itself is that we have this check clients function that we call for that checks every single connected file descriptor that might have data on it. And very importantly, we keep track of this pool of information about every single connection that we might have for us. In a normal threaded or multi-process program, we wouldn't have to keep a separate data structure manually ourselves for every single different thread. We'd simply say, oh, you create another thread, it'll have stack local variables, it'll keep track of it. When I switch to that thread, I will have those variables available to me and I will be able to run. I wouldn't even have to think about the fact that I've got to modify those variables in order to get any one specific thing done. But when everything is mashed together in the same main thread, you need to keep track of these things yourself. And so that's why in our pool data structure, We have global information about our entire server, like the number of file descriptors we care about, the highest numbered file descriptor, this ready set and this read set that we're going to talk about in a moment, as well as a set of file descriptors, one for every single connection that we could potentially have, and then a set of receive buffers for keeping track of what state a conversation is in, and a set of state variables for this receiving event to say, oh, am I waiting to send more bytes to this connection, or is this connection just a regular HTTP connection that's going to send me a request, I'm going to send a response, and I'm going to cut it out. So what matters here is not necessarily the fact that we have all these different variables. A lot of these variables are implementation specific for the task we're doing right now. But the higher level thing that I really want to point out here is that a lot of this stuff we're keeping track of one per hypothetically connected client. And so every single client is going to have its own file descriptor. Every single client is going to have its own receive buffer. Every single client is going to have its own receiving events flag. And we are going to keep track of which one of these clients we're talking to rather than relying on the operating system to keep track of it for us. So now we jump back down here to select. So that's our data structure that we're using. Now we're back down here where we're selecting in the main event loop. Let's take a look at check clients really quickly. So check clients is going to take a given set of file descriptors, and it is going to iterate through every single one to say, hey, am I supposed to read from this one? If I am supposed to read from this one, do that reading, do whatever writing you're supposed to do. And if you do need to, move that connection from state X to state Y for whatever that state would be. A lot of the times when I work with event-driven IO multiplexed systems in Select, it's really, really useful to think about it as a state machine where you move from one state to another state based on what events are happening. You need to keep track of those states because you don't have different stacks that will keep track of it for you kind of automatically. You have to do that yourself manually. So the other important thing that we have within this one specific function is that it's going to iterate through every single file descriptor that's hypothetically connected, and it's going to check, have I dealt with every single connection that has shown up for me at this moment in time? That's what this is for. Here we're saying, okay, when the read set comes back and tells us, hey, these are the file descriptors ready for reading, we're going to know 3 of them or 5 of them or 1 of them is ready. And we only need to go through this for loop a certain number of times, 1 for every single file descriptor that's ready for us to read data from. So when we do get to an individual client that is ready to be read from, we're going to run the body of this for loop. And here we're going to pop out our state and use that state. So here we're saying, okay, I know I need to work with client FD sub I. I know I need to work with receive buffer sub I know I need to work with the offset that is for, offset sub I, basically. So that way I have basically restored the state of this one specific client into these local variables to do what I need to do. Now this sounds like a whole bunch of very complicated stuff for not a lot of benefit, but the really, really powerful thing that we're getting out of this is that we are in complete control. We decide what needs to happen at any given point in time. And if we're running through this and we've got 5 or 10 or 15 or 50 different lines of code to run as a result of doing one specific connection, the great thing about this is that if we received other messages from other clients anytime while we were doing this, nothing would happen. We are in complete control of what code runs within our task until we decide, okay, now I'm going to start listening for other people to send me messages. That is one of the most powerful components of IO-based multiplexing, is that we can keep on working and not get interrupted until we choose to be interrupted again. So when we come in here to check clients, we're going to do everything we need for client 1 without stopping. We're going to do everything we need to do for client 2 without stopping. We're going to do everything we need to do for client 3 without stopping and being interrupted and having to put our work aside, go do something else, come back, and move on with our task. That is where we get a lot of the benefit out of using IO multiplexing as opposed to multi-threading or multiprocessing. Now, the final important component to this that I want to point out is the way that select returns its information to the user, because it is a very user unfriendly way to do things, but it's C, it was designed a long time ago. We didn't know nearly as much about how to make code easy to understand or easy to use as we do know now. But it's there and we got to learn how to use it. So let's go back to select. So as I mentioned back in the slides, when we pass our read set, our write set, and our accept set to select, we're passing it by reference. When we pass this information by reference to select, select is going to give us its return value by modifying the information that we pass into it. So if I say select, I really want to keep track of 1, 2, 3, 4, and 5. And if select recognizes that only 2 has data for us, we're going to pass in that reference to 1, 2, 3, 4, and 5 are all set within that FD set. Select is going to get rid of all of them except for 2. It's going to hand it back to us and say, here, these are the ones that are ready. If we were using that data structure to keep track of which clients are still connected, all that information would be gone. So it's really, really important that before we actually pass these pieces of information to select by reference, we need to copy things into kind of a temporary variable before passing it in. And so that's what this line 132 does right here. We keep track at a long-term level of who we care about in the data structure read set. And it's a set of data, and so we can copy it using equals. That all work. We can copy it using assignment. No big deal. We don't have to mem copy or string copy or anything like that. We simply say, take the data in this struct, copy that data through to this other FD set struct called ready set, and pass that in. So we're basically saying, this is our permanent version, this is our temporary version, and in any select code you write, you're almost always going to have something that looks a little bit like this. And if you care about your write set and your accept set, you're going to need to do the same thing for those. They're all going to have their own individual set of references. And when we receive this information back from select, we're going to get high-level information back in the return value saying, hey, this is the number of file descriptors that are ready total out of all the things you passed to me. And which ones specifically are ready are going to be here in this pool ready set. That is what has been changed, and that's what we need to inspect when we go through and run our code. So back to when should we be using I/O multiplexing? Just as a refresher, remember we use processes when we want to keep things very isolated. We use threads when sharing memory is good, or when we're trying to write parallel code that all has to do a similar task, but using multiple processors. And we want to use I/O multiplexing fundamentally when we have lots and lots of clients or tasks that are doing very, very small things that amount to not that much CPU work, but a lot of different work. So I/O bound tasks, tasks like running a web server or receiving interactions from a GUI. When we receive requests at a web server, we're getting hundreds or thousands of different, very, very small requests every second from all of the different clients around the entire world. What we really want to do there is just do a little bit of this one, not be interrupted, move on to the next one. Do a little bit of this one, not be interrupted, go as fast as possible, move on to the next one. So lots of high performance web servers work exactly like this. They keep track of their different connections and they manage which individual connection they service at any moment in time, rather than relying on the operating system to preempt different threads and say, okay, this one's going to run here. Oh, now I'm going to get rid of it. Even though it's not done yet, I'm going to spend all of the time and energy to swap this one out, swap this other one in, let it do its job, swap that one back out, swap that other one back in, let it finish its job. That's much less efficient than saying, let this one go all the way to completion, and then let this one go all the way to completion. You don't have as much unnecessary swapping. You have a much higher performance system, but you do have to write it yourself. It's also good to use I/O multiplexing when you're not dealing with any complicated locking. This is kind of the opposite of what I had mentioned in the previous video about threading, where if I want to have these threads deeply coordinate with each other, they're all doing roughly the same thing, but they're all using the same shared data. You're not going to necessarily want to use I/O multiplexing in a situation like that. One other big important component of I/O multiplexing is that it's always happening within one individual thread of control. If you want to use 4 different CPUs to handle 4 times as many people, 4 times as many requests, what you'll typically do is fork 4 different processes and have each of those different processes accept connections at the same time from the same socket and handle them completely independently in different processes. There we're composing these 2 different things, where we're saying processes give us a lot of isolation, which is very good. And I/O multiplexing gives us a lot of performance, which is good. And we can combine those two together to create a highly efficient, say, web server framework that can serve hundreds or thousands or hundreds of thousands of connections per second. Really, really awesome. What's important for this slide is that those individual tasks are very often completely independent of each other. They don't have to coordinate in any complicated way to get their job done. And finally, we don't need any isolation between these tasks when we're doing I/O multiplexing. As we saw in that code, all of that data is right there in that one data structure. It's all there. It's all there for that one process. We don't have any sort of isolation between a request for Chris versus a request for somebody else. And if they interact with each other, if something unexpected happens, all of that data is available and visible to the code that has been broken by somebody's malicious work. Right? There's very, very little isolation between these different connections when we are using an I/O multiplexing based approach to coding. So just as a little aside here at the end of this video, I want to talk a little bit about easier ways to do this. So as we saw, select is a bit of a bear to use. It's complicated. It requires a lot of boilerplate code. It requires thinking like the operating system to a certain extent. But as programmers, it's very, very often the case that we really like thinking iteratively. Like we're thinking we're going to do this step, then this step, then this step, then this step. And so there are a lot of different programming models that can actually give us the benefit of an I/O multiplexing based system, but without having to require us to do that. We can actually have the runtime or the compiler take care of this coordination for us without us having to get involved in it. The best example of that is, of course, JavaScript, because JavaScript does not itself have a built-in preemptive multitasking capability. JavaScript and its runtime runs your code in one thread until it is done doing whatever it's going to do. And it's going to say, ask the network to do something or ask for the user to give it more input. The old way to do this is with callbacks, where you say, and you can even do this in C, where you say, I'm going to do this task. And when this task is done, I want you, operating system, runtime, whoever's in charge, to say, after this long running task is done, call this function with the result of that specific task to keep doing whatever it is that needs to be done. That's the core event-driven way to do things. But if anybody has done a decent amount of JavaScript programming using raw callbacks, it gets really, really unwieldy, really, really fast. So you may have seen things like async and await. You may have seen things like futures or promises. These are all things that a runtime provides to us that makes it easier to do I/O multiplexing, where we run our code and we don't let anybody stop us until we choose to be stopped. And then we go do something that takes a long amount of time and then move on to whatever is next. Unfortunately, we're not going to have the time to go over those different paradigms in 361, but the important thing for us to remember for this course is that I/O multiplexing is this amazing race car that makes our code go faster by not being preempted and by allowing us to keep track of when different tasks start and when different tasks stop, but it's on us to keep track of those things as they are happening and making sure that everything works correctly. It's very often useful to think of these things as state machines and moving our connections through different states. And the code that we have in Homework 5 definitely has a good example of that in terms of a very, very basic set of states where you can either be waiting for a HTTP request to come in and then servicing it, or you can say this is a listening connection and I'm always going to want to send new bytes to it whenever somebody sends a chat message. That's just a very, very basic way of doing this. And doing it with select is very, very low level. We're very close to the way that the operating system does it. However, there are a lot of easier ways to do this that are provided by modern runtimes like JavaScript and Python, things like that, that allow us to get the benefits of I/O multiplexing without the complexity of doing select style programming. Thanks so much for watching, and I'll see you next time.